This is another video in the series for Math 1224 for UTSA. Today we're talking about 6.2, properties of power series. Building upon 6.1, where we had some properties of power series. Here are some more, and then of course some more things we can do with power series. So given some interval I, this will be an interval of convergence. Suppose that the series C sub n converges to a function f on the interval, and then also some series D sub n converges to another function g on that same interval. Okay, so two different series, each converging to some function on the same interval. The power series formed by C sub n plus or minus D sub n, in parentheses, times x to the n power, of course, converges to f plus or minus g, whichever you happen to have here is what you get in the functions, on that same interval. For any positive integer m and any real number r, the power series formed by r times x to the m power times C sub n times x to the n power. That forms a new power series, which is convergent to, or converges to, r times x to the n power times f of x on the interval I. Again, for any positive integer m and any real number r, the power series formed by C sub n times r times x to the n power, in parentheses, to the n power, that converges to f of r times x to the n power for all x such that r times x to the n power is in the original interval. So what does all that mean? Basically, there's sums and differences of series. We can have a series times some power function. We can have a series with a composite form of some power function, basically. So let's do some examples. We're going to find a power series representation for f of x equals 1 over 1 minus x plus 1 over 1 plus x, okay? There's more than one way to do this, but I want to do this in the most straightforward way possible, to start with at least. So this example is just the geometric power series we've seen before. In this case, C sub n would be 1. So it's 1 plus x squared plus x cubed and so forth. This is a variation on that. I can rewrite this one as 1 over 1 minus negative x and do a substitution using this right here. I'm going to have negative x in the parentheses. So this will be 1 over 1 minus x plus 1 over 1 minus negative x. So I'm forming a composite with a power series that I already know. I know that this function is represented by the sum as n goes from 0 to infinity of x to the n power. So if I add to that the modified version plus the sum as n goes from 0 to infinity of negative x to the n power, that's forming the composite, okay? I know that this is a power series that converges to whatever, on whatever interval they both converge on. Now, we know that this one converges on the interval -1 to 1. This one will converge on whatever interval you have such that negative x is in that interval -1 to 1. So for this guy, the interval convergence is -1 to 1. And for this guy, this is going to be all x such that negative x is in the interval -1 to 1. So I'll say that -1 is less than negative x, which is less than 1. I can multiply each component by -1 and get 1 is greater than x is greater than -1. And that's the same interval as this. X is between -1 and +1. So this is a power series convergent on the interval -1 to 1. Now what I can do is I can rewrite this in the following way. I can say, okay, this is the sum as n goes from 0 to infinity of 1 times x to the n. So like I said earlier, C sub n is 1 plus the summation. The summation as n goes from 0 to infinity of -1 to the n power times x to the n power. Okay, this is basically C sub n here and D sub n here. So I can add these two series together and get the series as n goes from 0 to infinity of 1 plus -1 to the n times x to the n. So in this case, 1 plus -1 to the n power, that is my new C sub n, if you want to call it that. This is what was previously called C sub n plus D sub n. So what does that series look like? Let's do a few terms. Well, if n is 0, right, I'll have 0 here. -1 to the 0 power is 1. So 1 plus 1 is 2. So I'll have 2. And then, of course, when n is 0, x to the 0 is 1. Okay, what if n is 1? So plus, if n is 1, then this is going to be -1 plus 1 is 0. So when n is 1, c sub n is 0. So I don't have anything. I don't have a term at all. I'll go ahead and write 0. Plus, what about when n is 2? Well, 2 as an exponent means we have -1 squared. So that's 1 plus 1 would be 2. So I have 2x squared. Plus, what if n is 3? Well, 3. If I'm cubing -1, I have -1 plus 1 is 0 again. Plus, we're going to get 2x to the 4th plus 0 plus 2x to the 6th, and so forth. So basically, we only have even exponent terms. So I could write this if I want as 2 plus 2x squared plus 2x to the 4th plus 2x to the 6th plus ... So if I want, I could write this as the series as n goes from 0 to infinity of 2 times x to the 2n power. If I want something more compact, this is an equivalent way to write the same thing if I want to do it that way. Okay, next example. Find a power series representation for f of x equals x squared over 1 plus x squared. Okay, so basically there's two properties I have to use here. I'm going to rewrite this as x squared times 1 over 1 minus negative x squared. So I'm using a composite. I'm plugging negative x squared into 1 over 1 minus x. I'm also multiplying by x squared. So I'm using both the composite property. This one here, I have a composite in the exponent, and I'm multiplying against it as well. Okay. So this will be x squared. Well, there's several ways to write this. I guess I'll do it this way. This will be the sum. This will be the sum as n goes from 0 to infinity of x squared times negative x squared to the n power. Okay. Now, if I want, I can write it like this. I could leave it this way, but that's a little messy. I've got x in two places. So if I want, I can write it like this. So x squared times -1 to the n times x squared to the n power, which I could write as sum as n goes from 0 to infinity of -1 to the n times x squared to the n plus 1 power. And if I want, I could do it this way. If I want to do it that way, I can do that. So something we didn't do with the first example, let's go ahead and do it with this one, is I want to look at a graph of this and see, does this really look like the right representation? Let's switch over to Desmos here. And if we look at, this is the standard one where c sub n is 1 and we're approximating 1 over 1 minus x. And you can see that we have the red bit of the graph, and then I have the blue. This is the graph of the power series with n equals 0. So this is just n equals 0. Little n goes from 0 up to big N, and big N is 0 in this case. So as I increase this, you can see that basically the partial sum, the 50th partial sum, is a very good approximation of the function, right? Now, I didn't do this with the first example, but that's okay. So if I go up here and I change this to be plus x squared on bottom and then x squared on top, and then I change c sub n, this needs to be -1 to the nth power. And then also here in the exponent of x here, I need to do 2n plus 2. Okay, so there is just the first term of that series. As I increase n, you can see that the section on which the graph really matches gets larger. Let's do that again. Let's back it up. Here is this is basically the 0th partial sum of the power series. And as I increase n, the interval on which the blue curve matches the red curve gets wider. So that's basically S50, the 50th partial sum. You can see that it matches the graph really closely. Let's actually go back and do the first one as well. I just forgot to do that one. So if I go up here and we do, let's see, 1 over 1 minus x plus 1 over 1 plus x, right? That's what we had. And then C sub n, that's going to be, what do we have that as? That was, let's start this over. Okay, so 1 plus negative 1 to the n power. Yeah, that's what we had. Okay, so now if I, oh, I should have backed that up. So also here I have to change this. This is just x to the n, again, as before. Okay, where is it? There it is. Okay, so there's the graph in red of 1 over 1 minus x plus 1 over 1 plus x. Okay, so now as I increase n, this blue line should change and it should start to match. And see, indeed, it does match really well. In fact, if I only do a few terms, it matches really well. And you can see up here, it doesn't quite reach, but if I increase it, you can see that it then matches the curve. So yeah, so that's a really good representation for that. Okay, so let's go ahead and go back to our next example. Okay, so that's the one we just did. We wouldn't graph that one. Okay, and then that was the second example. So let's go do another example. So let's find a power series representation for this function. Now, there's actually two ways to do this one. One of which we haven't gotten to yet. We haven't gotten that property. So we're going to use the approach for which we do have a property, of course. So for this one, because I want to use the sum property, I need to write this as a sum of two functions. So I need to use a partial fraction decomposition. And there's two ways to get started. I'm going to do a over 1 minus x, because this denominator has the format that I want for my power series, plus b over 2 minus x. And you might notice two things. One, hey, that 2 is not part of the power series that we already know, but that's okay. We'll deal with that. And then also, well, sure, this matches the power series we already know about, but we don't have that. Well, that's going to be okay, too. Don't worry about that. So what I'm going to do is I'm going to copy this, and I'm going to modify it a little bit. I'm going to say, you know what? I'm going to multiply top and bottom by -1. I'm going to switch the order of this factor while negating the top. Okay, so I'm going to have minus here, plus here, so that really these two are the same thing, right? So I can even go forward and say, oh, let me rewrite this as 1 minus x. Okay. So now I'll multiply both sides by the denominator on the left. So I'll have -1 equals a times 2 minus x plus b times 1 minus x. So -1 equals 2a minus ax plus b minus bx. So on the right, I'll combine like terms. So I'll have -a minus b times x plus 2a plus b. And on the left, I'll have 0x minus 1. So I know that 0 has to equal -a minus b, and -1 has to equal 2a plus b. So in this first equation, I'm going to add b on both sides. So b equals -a. And I'm going to substitute that into this b here and get -1 equals 2a minus a, which of course is a. So a equals -1. And since b is -a, b is 1. So a equals -1, b equals +1. So I want to come with a power series representation for -1 over 1 minus x plus 1 over 2 minus x. Now, before I make the representations, I have to do something, a little bit of a modification. This one's easy. I'm just going to move that -1 out in front. I'll have -1 times 1 over 1 minus x. Here, I need to do something a little bit harder. I need to factor 2 out of the denominator and write a 1/2 in front. So I'm going to have 1/2 times 1 over 1 minus x over 2. So this is -1 times 1 over 1 minus x. So I have -1 times the geometric power series we already know about, plus 1/2 times 1 over 1 minus x over 2. So this is 1/2 times a composite of the power series that we already know. So I'm going to be able to represent these with the following. -1 times series as n goes from 0 to infinity of x to the n plus 1/2 times the series as n goes from 0 to infinity of x over 2 to the n power. Okay, now I want to rewrite this as a single power series, so I have to do a little bit of rearrangement. I'm going to go ahead and put the -1 inside here and the 1/2 inside here. Okay, so I'm going to have sum as n goes from 0 to infinity of -1 times x to the n power plus the series n goes from 0 to infinity of 1/2 times 1/2 to the n power times x to the n power. Now what I'm going to do is say, oh, well, here's my c sub n, here's my d sub n. I can add them together into a single series. So I have the series, and I guess I should be saying this is equal. Series as n goes from 0 to infinity of -1 plus, I'm going to rewrite this as 1/2 to the n plus 1 power. So 1/2 to the n plus 1 power times x in power. So this is my new coefficient based on n. So let's go back to the graph and see if this looks right. So our function was 1 over x minus 1 times 2 plus x. So 1 over x minus 1 times 2 minus x. Okay, so there's our function. Let's hide that for now. So there's our function, right? It's got asymptotes at 1 and at 2. So now c sub n, this is going to change to, yeah, I guess I can leave this overall structure here. So -1 plus 1/2 to the n plus 1 power. Oh, yeah, you have to be careful with, Desmos doesn't like to make exponents with the sum, so you have to fiddle with it a little bit. So that should be it. Let's change n down to 0. Let's turn this back on. Oh, okay, so here you can see that the blue section goes through the red curve. And as I increase n, the right-hand side, converges very quickly, right? It matches the function very quickly. The left-hand side flops around a little bit. It changes degree, essentially. Goes up and down, up and down, up and down. But basically, the right-hand side converges very, very rapidly to match the function value. Here on the left, if I reduce n, you can see that only up to about -0.4 does it match very closely, or -0.3 really. If we increase n a little bit, oh, now it matches up to -0.6. If we increase n some more, oh, now it matches up to -0.8 and so forth. So when we get this far, it matches up to -0.87 or so, something like that. And of course, when n goes to infinity, it matches perfectly. It'll just match the function entirely. Okay. We actually forgot to do something with this one. We didn't think about the interval of convergence. So, of course, this one converges on the interval -1 to 1, as we've seen before. What about this one? Well, this one converges for all x, such as x over 2 is between -1 and +1. So if I double every component there, I'll get -2 is less than x, which is less than 2. So this series converges between -2 and +2. This series converges between -1 and +1. And you always basically take the intersection of the two series, or in other words, whichever one is smaller. So this was -1 to 1, or in other words, -1 is less than x is less than 1. So this one is larger, so we're going to use this one. So the interval of convergence for this one is -1 to 1. What's next? Multiplying power series. So this gets fairly complicated. So for some interval I, suppose that the power series C sub n converges to some function of f, and power series D sub n converges to some function, or some function g on the same interval, both on I, same interval. Then let E sub n equal this sum. So C0 times D sub n, C sub 1 times D sub n minus 1, C sub 2 times D sub n minus 2, C sub n minus 1 times D sub 1, and then C sub n times D sub 0. Notice that the subscripts add up to n in each case. 0 plus n is n. 1 plus n minus 1 is n. 2 plus n minus 2 is n. N minus 1 plus 1 is n, and n plus 0 is n. Okay? What you're doing is you're taking, basically, if you look at say, and little n was 5. You look at the first 5 terms of the first series and the first 5 terms of the second series, and you pair them up, but you move forward through the first list and backward through the second list. Okay, so you go C1, D5. C0, C0, D5, C1, D4, C2, D3, and so forth. Okay, until you got down to C5, D0. Okay, which you can summarize this way. Okay, so there's a formula that will give you any of those for whatever n value that you want, if n is 5 or 10 or 1,000 or whatever. Then the product of the two series will be the sum of those pairwise combinations, which converges to f of x times g of x on the interval. Okay. Like I said, this is fairly complicated. So let's look at an example. So for this one, we probably could use a partial fraction decomposition, but instead, let's do this. We're going to write this as 1 over 1 minus x times 1 over 1 minus x squared. We'll come up with a power series representation for each one. Well, this one, you kind of already have it. But then we'll multiply those two power series representations. So, of course, 1 over 1 minus x, we'll represent this with the series as n goes from 0 to infinity of x to the n, and this converges on the interval -1 to 1. The series 1 over 1 minus x squared will represent this with the series as n goes from 0 to infinity of x squared to the n power, which we can write as the series as n goes from 0 to infinity of x to the 2n. And the interval of convergence for this one is where x squared is between -1 and +1. Now, since x squared is not negative anyway, we can drop that condition. So we'll just say x squared is less than 1. We can apply the square root function to both sides. So absolute value of x is less than 1, which gives us x is between -1 and +1. So the same interval as this one. So we don't have to worry about, how do we decide which one to use? Well, they're the same anyway, so just use the one that they both have. So I want their product. So f will be the product. Series n goes from 0 to infinity of x, the n power, times series n goes from 0 to infinity of x to the 2n power. Okay. Now, if we really wanted to, we should be able to come up with a formula for the coefficients of the new series as a function of n. Let's not do that. Let's just write out the first few terms of the series. So this first factor, this will be 1 plus x squared plus x cubed plus x to the fourth plus, let's say x to the fifth plus dot, dot, dot. Okay. This one, only even exponents. When n is 0, the exponent is 0. When n is 1, the exponent is 2. When n is 2, the exponent is 4. When n is 3, the exponent is 6. So this will be 1 plus x squared plus x to the fourth plus x to the sixth plus x to the eighth plus, well, we're out of room, dot, dot, dot. Okay, so basically we're going to do an elaborate version of foiling. I'm going to multiply 1 by each of these and write that down here, okay? And then we're going to multiply x squared by each of these, and we'll write it in a new line below that. You'll see what I mean. So this equals, well, 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth plus, let's do 1 x to the sixth plus dot, dot, dot. That's fine. Maybe we'll erase this and put more in later. So now I want x squared times each of these. So x squared times 1 would be x squared, times x would be x cubed, x to the fourth, x to the fifth, x to the sixth, and so forth. And I'm going to write this starting here under x squared. Okay, then x to the fourth times this would be x to the fourth, x to the fifth, x to the sixth, x to the seventh, and so forth. Then x to the sixth times 1 would be x to the sixth, x to the seventh, x to the eighth, x to the ninth, and so forth. I think I will end up putting a few more in there. Okay, so after we add all that up, we've just got here 1 plus x. I have 2 copies of x squared, and I have 2 copies of x cubed. So plus 2x squared plus 2x cubed plus. I have 3 copies of x to the fourth and 3 copies of x to the fifth. I have 4 copies of x to the sixth. Why don't you pause the video and think about, and maybe it doesn't take that long, how many copies of x to the seventh do I have? Well, I have 4 x to the sixth plus, well, 4x to the seventh plus 5x to the eighth plus 5x to the ninth plus dot, 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 right? And then 6x to the 10th, 6x to the 11th, and so forth, right? So if I wanted a formula for this, and I didn't quite write it this way, there's a 1 there, right? The first 2 terms have the same coefficient. Then the third and fourth term have the same coefficient. And then the next 2, and the next 2. And it might not be clear what to do, and there's a couple things to try, but here's the formula. And there's at least 2 ways to write this. So n goes from 0 to infinity. So I want to point out 2 functions, and we can use either one, but I'll point them out over here. The floor function does this. If you plug in something like 2.7, it rounds down to the nearest whole number, okay? The ceiling function does the opposite. It rounds up to the nearest whole number. If you plug a whole number to either one, nothing happens. But basically, floors round up, floors round down, ceilings round up. So 2.7 is still rounded up for floor, or rather down for floor. 2.1, the ceiling of that is 3. You round up, okay? So what we could do is say this. I'm going to take the ceiling of n over 2. So take half of whatever n is and then round up. Will that work? Maybe not. Nope, nope, nope. Let's do this. Let's do floor of n over 2 plus 1. That'll work. Okay, x to the n. There we go. That should work. We might have to amend that. We'll see. So let's switch to Desmos and see what it looks like. There's our previous example. So let's get rid of that. So this would be 1 minus x squared. Let's put that example away. Okay. Now c sub n, I said would be floor, which Desmos does recognize, of n over 2 plus 1. Okay. So you see that blue line goes through the red curve. If I increase n, now it's slanted, and you can see the right-hand side very quickly matches the graph. The left-hand side, not quite as well. That's only at n equals 8, and as I increase this, you can see that this bit where the graph curves back down, this bit here is basically going up. And as I increase that, it matches better and better and better. In 50, it matches quite well. Okay, if I back it off to 49, because of the degree involved, the degree being odd, this has to curve back down. It has to be basically an S shape because the degree is odd, right? Whereas when the degree is even, it's a more or less a U shape, okay, from polynomials. So yeah, that seems to match really well. So what's next? Now, okay, differentiating and integrating power series. This is really useful because this allows us to basically come up with power series representations for functions we don't otherwise have easy ones for. It also allows us to find derivatives and antiderivatives for functions that maybe we don't really have a good way to deal with them directly, but we can do it through a power series. So suppose the power series c sub n times x minus a to the n power. We had been assuming a was 0 earlier. In a later section, we're going to want to not do that, make that assumption. So we're reintroducing the center being at some arbitrary number now, because in the next section, we'll do a little bit of that. So suppose this converges some function f on the interval I equals a minus r to a plus r for r some positive real number. Then the function defined by f of x equals c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared plus c sub 3 times x minus a cubed. This is the power series. Is both differentiable and integrable on the interval I. F prime can be found by differentiating the series term by term. So f prime equals the series as n goes from 0 to infinity of c sub n times x minus a to the n minus 1 power. This is just the power rule for the derivative. That's all you got to do, term by term. So you get c1, because c0 went away, right? The derivative of a constant is just 0. The derivative of a linear term will just be the slope, so c1, plus 2 times c2 times x minus a, plus 3 times c3 times x minus a squared, and so forth. Okay, there's the derivative. That's it. And this converges on the same interval as the original function. The antiderivative can be found by integrating the series term by term. So the antiderivative of f of x dx is the series as n goes from 0 to infinity of c sub n times x minus a to the n plus 1 power divided by n plus 1. That's just the power rule for antiderivatives, right? And you get c0 times x minus a, c1 over 2 times x minus a squared, c2 over 3 times x minus a cubed, and so forth, which converges on the same interval, okay? So we're going to use the power series representation of f of x equals 1 over 1 minus x to find a power series representation of g of x equals 1 over 1 minus x squared. We could probably try to separate this using a partial fraction decomposition. Maybe we could try that. Maybe we could treat this as a product of two power series. We could try that. That would probably work. But let's make this a little bit easier for ourselves and just use the fact that this is the derivative of this, right? G of x equals f prime of x, right? So we want the derivative of the power series n goes from 0 to infinity of x to the n power, and we just do the derivative term by term, so we get the series as n goes from 0 to infinity of n times x to the n minus 1 power. There we go. That's it. We didn't need the partial fraction decomposition. We didn't need to deal with a product and trying to work out term by term what is the new coefficient function as a function of n. Just use the derivative. So let's go take a look at that. So let's hide that for a second, get rid of that. Now, the coefficient function is just n, right? We are looking at this squared, minus x squared. And I need to change here the exponent to be n minus 1 because of the power rule. Okay. So now if I go back to showing this, you can see that's not really very accurate, but I think that's fine. Don't worry about that. As soon as we go to n equals 2, now this goes through the function. As we increase this, on the right-hand side, it very quickly matches up. On the left-hand side, it slowly, see, here it's accurate at about negative 0.5. As we increase, oh, it's accurate now at about negative 0.7. Increase, oh, it's accurate about negative 0.82 or something like that. On the right, it matches, very, very clearly, right? It matches the graph very clearly. On the left, well, it does, but we're only doing 50 terms, well, 51 terms, right? Since we started 0. So, yeah, but if you have the series as n goes to infinity, you have the entire series. Well, this won't happen. This will go all the way to the end. This will go all the way to the end. In fact, let's see if we can increase this to 100 and see if it likes that. It might not. We'll see. So yeah, it gets up to about negative 0.9. It gets closer, and that's only doing 100 terms. Well, 101 terms up to and big N equals 100. So hopefully you can see that. Yeah, that is a way to get a function that matches that a power series representation of that function. You've got a power series that gives you the function values on the interval of convergence. Okay, so let's go do another one. So we're going to find a power series representation for f of x equals ln of x plus 1. Okay. So we know that f prime of x equals, well, 1 over 1 plus x, right? That's the derivative using the chain rule, which this can be written as 1 over 1 minus negative x. Oh, so this is a composite of the geometric series, okay? So f of x, this will be the antiderivative of f prime of x dx, okay, which is the antiderivative of the sum as n goes from 0 to infinity of negative x to the n power. I guess I should put a dx here. We'll do it term by term. Of course, the interval of convergence is whatever interval such that negative x is in the interval negative 1 to 1. So negative 1 is less than negative x, which is less than 1. Negate all those components. So 1 is greater than x, which is greater than negative 1. And that is the same interval of convergence as the original function, which should not be surprising. So this will be the series as n goes from 0 to infinity of, well, there's two ways to do this. So before doing this term by term, I'm going to do the following. And I probably should have parentheses. I'll write this in the following way. That's not necessary, I suppose, but that's the way I prefer to do it. So this will be sum as n goes from 0 infinity of negative 1 to the n power times x to the n plus 1 over n plus 1. So this is the series as n goes from 0 to infinity of negative 1 to the n power over n plus 1 times x to the n plus 1. Okay, so let's go graph this out and see if it really does look like the right result. So our function this time is ln of x plus 1. Let's hide that, take n down to 0. And my c sub n, this is -1 over n plus 1. I need an x, caps lock was on. N plus 1, this to the n power. And then also here, I need to change this n minus 1 to an n plus 1 to match what we had. Okay. So let's show this again. So you can see, oh yeah, it goes through the origin there. Good. And as I, oh yeah, it is ln, of course, plus ln of x plus 1. As I increase this n value, on the left, you can see it matches pretty quickly. And on the right, it matches pretty quickly as well. As I increase this, it matches even better. So on the left, it travels down. This is a limitation of the software, probably, that it stops right there. No, that's just a limitation of the sound, probably. But it's rounding quite a bit. And by this, I mean the limitation in the number of terms you're using. So this guy, this jumps up and down. And as I increase this, and this is basically because the 90th term is even degree, odd degree. If n is 90, then we'll have 91. So this is an odd degree. It has to curve up. You go to 91, then this is an even degree. It has to curve down, basically. And then the more terms you use, the more accurate it's going to be. So there is the power series representation for ln of x plus 1. So that's basically it. These are the basic tools that we need for later topics in section 6.3.